for reasons that we're going to talk about later. So nothing on the first midterm has to do with which enzymes in glycolysis are good regulatory ones or not. Yeah.
So ATP is needed to phosphorylate in the steam before?
Yeah.
Why don't we like draw ATP as things?
We could, but it's not used. It's only used once. Is the thing. So it's kind of like if we would use it. We would draw it as being used if it was consumed in the reaction every time the reaction happened. But because the enzyme is a multiple turnover enzyme, it's doing hundreds of them, so there's only one ATP for 100 products. Yeah.
We would draw it if we were drawing out the building of enzyme.
Yeah, absolutely. Yeah, right. This enzyme is made by protein synthesis in the cell like every other one, and then after it's made and probably folded up, specific kinase comes along. Phosphorylase cysteine. It's quite unusual, actually, to have a phosphorylase cysteine. There's not too many of those. Other questions? Okay, step 9 is enolase. And enolase is simply the removal of water from 2-phosphoglycerate to generate phosphoenolpyruvate, which you may recall from chapter 13 is yet another high-energy compound that can be used in a substrate level reaction to make more ATP. Right? So this is slightly unfavorable in the forward direction. It's also it's also easily reversible reaction though. The way this enzyme works is by virtue of a direct role of a metal ion in the active site. Okay, so we can call this a Lewis acid if you like. Although the terminology is sometimes ambiguous there, so it doesn't matter. What we have going on here is the breakage of a carbon-hydrogen bond by removal of this hydrogen by the lysine. Right? So that's a tough bond to break. Okay, so the enzyme has to bring a lot of catalytic power to bear on that. And the catalytic power that is brought to bear is the formation of this enolic intermediate here, where we see we have a negative charge and another negative charge here. Right? So this is not a carboxylate, right? Okay, so we've got double bond here, we've got two options. Both of them are carrying a negative charge. And so we've got magnesiums on there to compensate. Two magnesiums to compensate, which looks like a bit more than you might need. But remember, you've also got this multiply negatively charged phosphate right next door. So two magnesiums near each other in the active site. So you can think about how this active site might be constructed. Those two magnesiums can't be directly in contact with each other because otherwise you have too much positive charge right there. They have to be separated by something else. There might be different groups in there that ligate from the back here, keep the magnesiums 3 or 4 angstroms apart so that they're positioned to each bind on the oxygens. Okay, but that's the essential driving force, the presence of two magnesiums in there just to compensate that charge so that this tough bond can break. Okay. And then in the second part of the reaction, we have water removed to form phosphoenolpyruvate. Okay. Questions? Okay, the last step is just like step 7. It's another substrate level ATP synthesis reaction. The delta G0 prime is even more negative for this one. This reaction by pyruvate kinase forms pyruvate, which is a very important central metabolite in cells. So this is one you certainly want to remember the structure of going forward. This is actually an irreversible reaction. So that's it. That's glycolysis. We've made 4 ATPs. We've made 4 ATPs in the second part of glycolysis. So here we've made we made 2 here, we made 2 here. We used up 2 in the first part, so there's a net of 2 that's made. And there's also a net of 2 NADHs that are produced. And later on, we'll go on and learn how many ATPs can we get per NADH. Turns out that 2 NADHs can generate 5 ATPs in oxidative phosphorylation. So each one generates 2.5 ATPs. Not necessarily an intuitive number to think about, because if ATP were being made on an enzyme in a sort of normal way, you could never make half of one, right? And yet it's 2.5 ATPs per NADH is the way it works. Any questions about the overall pathway? I want to talk a little bit about the overall thermodynamics. So here's glucose. So this is the overall reaction of glycolysis. If you just look at all 10 steps together and put them in one place. Okay. Glucose, NAD, ADP and phosphate. Right. Glucose and pyruvate. If you were to write every step, of course, all those intermediates would just cancel out. So the only carbon we have is 1 glucose and 2 pyruvates, right? NAD goes to NADH plus H plus. That's the way the mechanism works. NAD goes to NADH plus H plus. We may have time to look at that. And then 2 ADPs, 2 phosphates, 2 ATPs, and also there are 2 waters produced. Okay, because water is removed in the enolase reaction. So what are the thermodynamics of this? Right? If we look at glucose going to 2 pyruvates, right, how much energy of glucose have we really been able to extract? So one way to look at this is to ask, well, how much more oxidized is pyruvate than glucose? And the answer is not a whole lot more oxidized. It's a little more oxidized, but not much. In particular, there's no CO2 has gone off, right? We've not lost any CO2, so we've not driven any of the carbon molecules in the 6-carbon glucose off into the most oxidized form yet, which is clearly how we can derive the most energy. So we would predict, just based on these considerations, that we're not actually getting a whole lot of energy out of this yet. And that would be right? We're only getting about 5%. So the overall delta G, these now standard state numbers for glycolysis, is about minus 85 kilojoules per mole, because we made 2 ATPs, right, out of it. That's plus 61, 30.5 for each one. The net of 2 ATPs are made, so that cost us. Right? The net that was actually available, if we don't consider that, was minus 146. But the total delta G from fully oxidizing glucose to carbon dioxide and water in oxygen is over 2,800 kilojoules per mole. Right? So we got about 5% out. So you can see the driving force in evolution to evolve pathways that were capable of transferring electrons from fuel molecules all the way to oxygen. Right? Because your yield, your energy yield just went up by a factor of 20 or so. So organisms that have to live anaerobically, I mean, life is possible. It's happening all over the place, but it's kind of slow and subdued, I guess you could say, compared to, you know, the active life you get, the active energetic life you get when you get to burn things in oxygen. Questions? Okay, let's move on. All right, so a couple more things to talk about to kind of put some more shape around this. We've gone through the whole pathway, so we now have a pretty detailed sense of what it takes to at least partially burn glucose to make pyruvate, and that will then go on in aerobic metabolism. We saw